This lesson is over symmetry. Symmetric with respect to the x-axis. Looking at the graph, notice it appears to be a reflection as if in a pond or a lake. But let's look at a real picture. So here we've got a picture of the sky above a pond or a lake. And we're going to look at certain places in the picture. Notice each point has its reflection being shown in the lake. Well, if we're thinking of this as points, what value is changing? Is it the x value or is it the y value? Well, notice it is the y value. The y value is now going down, so it now becomes a negative y. So we can see this visually. But what if we don't have a picture? How do we do this algebraically? To do it algebraically, we simply replace y with a negative y, and the new equation must be equivalent to the original. So we've talked about symmetric with respect to the x-axis. Let's now talk about being symmetric with respect to the y-axis. Here we've got a graph that looks like a parabola. And in this case, it is a reflection, but this time it's more like a reflection in a mirror. So let's look at a real picture. In this picture, we have a cat looking in the reflection of a mirror. Now again, I'm going to find several points in the picture and find its reflection. Now imagine this was a real XY axis kind of a graph. What value is changing? Is it the x or the y? Well, it's actually, this time, the change happens with the x values. It's now the opposite x value. It's going to the left or the different direction. So we can see that visually, but what about algebraically? Well, just like we found, it simply means you will replace the x value with a negative x, and the new equation must be equivalent to the original equation. Now, what must be left? We've already talked about the x-axis and the y-axis. Well, next is symmetric with respect to the origin. So here we've got a graph that looks like a cube. Now, for it to be symmetric with respect to the origin, it means the graph would need to rotate 180 degrees and look like the original graph. So imagine this picture, this image we have right now, and if you take several points and you see its reflection across the origin, notice what values are changing. Well, it turns out in this case, it's not one value, it's both values. The x now becomes a negative x, the y now becomes a negative y. So algebraically, it means we replace the x with a negative x and the y with a negative y, and the new equation must be equivalent to the original equation. Let's look at an example. Example 1 says, determine whether symmetric to the x-axis, y-axis, and origin. Looking at graph A, it appears to be a sideways facing parabola. And so first we were being asked to determine if this is symmetric to the x-axis. In other words, is this a reflection in a lake or a pond? Yes. Now, symmetric to the y-axis means, is this symmetric as if looking in a mirror? Is this a mirror image? No. Now, to determine if it's symmetric to the origin, it means if I were to rotate this graph 180 degrees, would it look just like the original graph? No. So this is not symmetric to the origin. For B, we have a different graph. It kind of looks like a W. we're going to see if it's symmetric to the x-axis. That means, is this a reflection in a lake or a pond? No. The y-axis, is this a reflection as if looking in a mirror? Yes. For the origin, if we were to rotate this or turn the graph upside down, would it look the same as the original? No. So it is not symmetric to the origin. For C, we have a graph that looks kind of like an S. Now, to determine if it's symmetric to the x-axis, is this a reflection as if looking into a lake or a pond? Do we see the same thing above the x-axis as we see below? No. Now, is this symmetric to the y-axis? Meaning, does it see its mirror image as if looking in a mirror? No. Now, to determine if this is symmetric to the origin. If we were to turn this graph and basically turn it upside down, would it look the same as the original? Yes. So this is an example of being symmetric to the origin. For D, we have the given graph. Is this symmetric to the x-axis, meaning does it see its reflection in a lake or pond? Yes. Is this symmetric to the y-axis, meaning does it see its mirror image in a mirror? Yes. Now, to determine if it's symmetric to the origin, you take the graph and rotate it 180 degrees, or if you were to turn it upside down, would it look the same as the original graph? Yes. So notice we've looked at several examples. It could be yes to one and no to the others, or it could be any combination of yeses and nos. But what happens if we don't have a graph? We only have an equation. Well, let's look. Example E, we have 5x minus 5y equals 0. Now remember, we're still being asked to determine whether if this is symmetric to the x-axis, the y-axis, and the origin. So we need to test them individually. First, we're looking at the x-axis. Now refer to your notes. In order to test if it's symmetric to the x-axis, we replace y with a negative y. So where y was, we take it out, put parentheses, and now plug in a negative y. What we're going to do is specifically look at the signs. And so negative 5 times negative y, we know a negative times a negative creates a positive. Our new equation is 5x plus 5y equals 0. Now what we need to do is compare this equation to the original. Is it the same? No. Notice that sign in between is not the same, which means this is not symmetric to the x-axis. Now we're going to test to see if it's symmetric to the y-axis. Again, looking back at your notes, for it to be symmetric to the y-axis, we simply replace x with a negative x. And so a positive 5 times a negative x gives us negative 5x, and then we still have minus 5y equals 0. Compare this equation to the original. Is it exactly the same? No. Notice there is one sign that is different. So since this is not the same, this is not symmetric. Now, for the origin, again, look back at your notes. This time it says to replace x with negative x and y with negative y. So we do replace both of them at the same time. Well, positive 5 times a negative x gives us a negative, and then negative 5 times a negative y gives us a positive. So our resulting equation is negative 5x plus 5y equals 0. Comparing this to the original, we see it's not the same, but is there anything we can do to make it look like the same equation? Well, in this case, I'm actually going to divide every single term on the left and right side by negative 1. And so Negative 5x divided by negative 1 creates a positive 5x. Positive 5y divided by a negative 1 is a negative 5y, and 0 divided by anything is 0. Now compare this to the original. Is it the same? Yes. Since it is the same, this is symmetric to the origin. All right, looking at example F, we have y to the third power equals 2x squared. Again, we're being asked to find if it's symmetric to the x-axis, y-axis, and the origin. For the x-axis, we simply substitute in a negative y for the y value, and then we check the signs. Now, negative y cubed means a negative y times a negative y times a negative y. We already know y times y times y will give us y cubed. What we're concerned with is the negative sign. A negative times a negative times a negative will always give you a negative. So our resulting equation is negative y cubed equals 2x squared. Now compare this to the original equation. Is it the same? No. So since we have one sign that is not the same, we simply say this is not symmetric to the x-axis. Now for the y-axis. This is your try it problem. Hopefully you found this to be symmetric to the y-axis. Now for the origin. This too is your try it problem. Hopefully you found this to not be symmetric to the origin. Example 2, find the point symmetric to the point negative 3, 2 with respect to the x-axis, y-axis, and origin. In these types of problems, there's actually two different methods you could use. The first method is the visual representation. So the first thing is we want to see what does this actually look like. So we take the time to draw an xy axis. From here, we plot the given point. They said find the point symmetric to the point negative 3, 2. So plot the point negative 3, 2. Since we have the graph and we see the axes, we go one by one. For it to be symmetric to the x-axis, we flip it across the x-axis and we find a new point. What is the name of that point? Well, that would be the point negative 3, negative 2. Next, we're being asked to find symmetric to the y-axis. So we go across the y-axis and we plot that point. And then we name it. What is the name of that point? Well, that would be the point 3, 2. Now, for it to be symmetric to the origin, it must pass through the origin, which would give us a new point. But what's the name of that point? Well, that would be 3, negative 2. And so there you have found your points that are symmetric to the x-axis, y-axis, and origin. Now again, that is only one method. The other method is to use the rules we just learned. The x-axis, we were given the original point of negative 3, 2. We learned that to find it symmetric to the x-axis, we simply plug in a negative y. All that simply means is negative is the same thing as the opposite. So look at your y value of 2. What is the opposite of a positive 2? Negative 2. So the corresponding symmetric point would be negative 3, negative 2. Now for the y-axis, again, we have the given point of negative 3, 2. But for it to be symmetric to the y-axis, we plug in a negative x. Again, negative just means the opposite of. So look at your x value. What is the opposite of negative 3? Well, that would be positive 3. And so your symmetric point would be 3, 2. For the origin, again, we're starting with the original point, negative 3, 2. And to find the symmetric to the origin, we have a negative x and a negative y. But again, that negative just means the opposite of. So the opposite of a negative 3 is a positive 3. The opposite of a positive 2 is a negative 2. Now, if you look at the points on the method 1, the visual graph, compared to method 2 using the rules, notice you get the same points. So regardless of which method, the point symmetric to the x-axis will be negative 3, negative 2. Symmetric to the y-axis will be 3, 2. And symmetric to the origin will be 3, negative 2.